Tonight, let's take a journey together. Not through physical space, though we'll travel further than you might imagine, but through understanding. Through the peculiar human quest to measure the immeasurable, to grasp distances so vast they seem to mock our very attempts to comprehend them. It's a journey that will take us from the fundamental nature of light itself to the edges of the observable universe, from the concrete to the nearly incomprehensible. Imagine for a moment that you're standing outside on a clear night, far from the glow of cities, where the darkness is deep and pure. Perhaps you're in the desert, or on a mountain, or in some remote countryside where light pollution hasn't yet erased the stars. Your eyes adjust to the darkness, and slowly, the sky reveals itself. First, the brightest stars emerge, then dimmer ones, and finally, if you're patient, thousands upon thousands of points of light spread across the celestial sphere above you. Look up at the night sky for a moment. If you're somewhere dark enough, away from city lights, you might see a faint smudge of light in the constellation Andromeda. It's not quite a star. It's softer, more diffuse, like a small cloud frozen against the black. That's the Andromeda Galaxy, our nearest large galactic neighbor, a spiral galaxy much like our own Milky Way. It contains roughly 1 trillion stars, clouds of gas and dust, dark matter, stellar nurseries where new stars are being born, and stellar graveyards where old stars have died. And the light entering your eye right now, the photons that traveled across space to hit the light-sensitive cells in your retina, left that galaxy 2.5 million years ago. Think about that for a moment. 2.5 million years. When that photon began its journey, Earth was a very different place. Our ancestors hadn't yet learned to make stone tools. They were Australopithecus, early hominids just beginning to walk upright on African plains, using their hands to gather food and perhaps fashion the most rudimentary implements. They had no language as we understand it, no art, no cities, no agriculture. They were just beginning the long evolutionary journey that would eventually lead to us. And above them, utterly unaware, these photons had already begun their journey across the incomprehensible darkness of intergalactic space. Those photons crossed a void that, for most of human history, we didn't even know existed. They traveled through regions where matter is so sparse that there's less than 1 atom per cubic meter of vacuum, more perfect than anything we can create in laboratories on Earth. They passed through the gravitational fields of countless stars and dark matter halos that bent their paths ever so slightly. They witnessed, in their way, the expansion of space itself, the stretching of the universe that has been ongoing since the Big Bang. And after all that time, after all that distance, a few of them happened to arrive at just the right place and time to enter your eye and be absorbed by molecules in your retina, triggering a cascade of neural signals that let you see. 2.5 million light years. The words roll off the tongue easily enough, but what do they actually mean? How can we wrap our minds around a distance described in years of light travel? What does it mean to measure space in units of time? And more puzzling still, more impressive in its own way, how did we, tiny creatures, bound to a small planet, gifted with minds shaped by evolution to handle much more modest distances, ever manage to measure such cosmic gulfs? These are not trivial questions. They cut to the heart of one of humanity's grandest achievements, our ability to comprehend a universe that vastly exceeds the scale of our everyday experience. We evolved to judge the distance to a predator, to estimate how far away water or shelter might be, to navigate through forests and across plains. We evolved for a world measured in meters and kilometers, distances we could walk in minutes or hours or days. Yet somehow, we've managed to extend our understanding far beyond those evolutionary constraints. We've learned to measure distances to stars, to galaxies, to the very edge of the observable universe itself. How? That's the story we're going to explore tonight. We're going to understand what a light year actually measures, not just the definition, but what it means, why we use it, how it connects to the fundamental nature of light and space and time. We're going to discover why light itself holds the key to cosmic distance, why the speed of light is so fundamentally important not just to physics, but to our entire understanding of the universe's structure and history. We'll see how astronomers built an elegant ladder of measurements, each technique extending the reach of the one before it, reaching from our solar system to galaxies billions of light years away. We'll understand parallax, the geometric technique that gives us the first rung of the ladder. We'll learn about standard candles, cosmic lighthouses like Cepheid variable stars and supernovae that can be seen across vast distances. We'll explore how the expansion of the universe itself becomes a measuring tool at the grandest scales. We'll discover one of the most profound truths in all of astronomy, that every distance in space is also a journey backward in time. When we look at distant objects, we're not seeing them as they are now, we're seeing them as they were when their light left them. Astronomy is the only science where looking farther out necessarily means looking farther back. Every telescope is, quite literally, a time machine, allowing us to observe the ancient history of the cosmos. And we'll confront the humbling truth that our brains, shaped by evolution for entirely different purposes, really struggle against the sheer vastness of it all. We'll see that there's a fundamental limit to human intuition, that some things can be known without being felt, measured without being truly imagined. The universe is larger than our minds can hold, and that's not a failure on our part. It's simply the reality of being small, conscious beings in a cosmos that extends far beyond the scales our ancestors needed to survive. This is a story about human curiosity meeting cosmic immensity. It's about the clever methods we've devised to measure what seems unmeasurable. It's about the interplay between observation and theory, between data and understanding. It's about how we extend our senses with instruments, our intuitions with mathematics, our reach with persistent, careful, meticulous scientific work spanning generations. And it's about finding peace, even joy, in the recognition that the universe is far, far larger than our intuitions can ever truly accommodate. So settle in now, get comfortable, let the tensions of the day fall away. We're going to travel, in understanding, if not in body, across distances that challenge the very meaning of the word far. We're going to explore scales that beggar the imagination, times that dwarf human history, spaces that make our entire planet seem like a mote of dust. But we'll do it gently, step by step, building understanding as we go. We'll start with light itself, with the fundamental speed that governs cosmic distances. We'll see how that speed converts time into distance, giving us the light year as a natural unit of measure. We'll climb the cosmic distance ladder, rung by rung. We'll grapple with the strangeness of look-back time, the way distance and history intertwine in astronomy. And we'll end with perspective, with context, with a sense of both our smallness and our significance. It's a journey worth taking. Everything we're going to discuss tonight begins with light. Not just because light years measure distance in terms of light travel, but because light itself is the fundamental messenger of the cosmos. Every bit of information we have about distant objects, every photograph, every spectrum, every observation, arrives encoded in light. Photons carry news from the stars, and without them, we would know almost nothing about the universe beyond our immediate vicinity. And light, it turns out, has some very peculiar properties that shape our entire understanding not just of astronomy, but of space, time. Let's start with a number, a very specific number, 299,792,458 meters per second. That's the speed of light in a vacuum, and that number isn't approximate. Since 1983, the meter itself has been defined as the distance light travels in 1/299,792,458 of a second. We've essentially used light to define distance, which tells you something fundamental about how important this speed is to our understanding of reality. The speed of light isn't just another physical constant. It's woven into the very definitions we use to measure the world. But let's make this speed more tangible, more real, because big numbers can be abstract and meaningless without context. In 1 second, the time it takes to say 1 Mississippi light travels far enough to circle the Earth 7.5 times. Imagine a beam of light starting at the equator and racing around the planet. It would lap the globe, pass its starting point, and do it again and again, 7.5 times, all within that single second. Or think of it this way. Light could go from New York to Los Angeles, coast to coast across the United States, and back again nearly 37 times in 1 second. The distance is about 4,000 kilometers each way, and light covers it in about 13 milliseconds. Faster than thought. Faster than anything we have everyday experience with. Or consider this, a nanosecond, 1/1000th of a second, is enough time for light to travel about 1 foot, roughly 30 centimeters. This isn't just a curiosity, it matters in the computers we use every day. Modern processors operate at speeds measured in gigahertz, billions of cycles per second. At those speeds, the physical distances between components matter, because even light takes measurable time to cross them. Engineers designing microchips have to account for the speed of light when deciding where to place different parts of the processor relative to each other. Signals, traveling at or near the speed of light, still take time to propagate, and that time matters when you're doing billions of operations per second. The speed of light is fast, incomprehensibly fast by human standards, and yet, on cosmic scales, it's actually rather slow. It takes light from the sun about 8 minutes and 20 seconds to reach Earth. The sun could explode, and we'd have 8 minutes of normal daylight before we'd notice anything wrong. Light from the nearest star takes years to reach us. Light from distant galaxies takes millions or billions of years. The universe is so vast that even light, the fastest thing there is, can seem almost sluggish, crossing cosmic distances. Humans have known that light travels fast for a very long time, but the idea that it had a measurable speed, that it wasn't instantaneous, was revolutionary. Think about your everyday experience. You flip a light switch, and the room illuminates immediately. You open your eyes, and you see. There's no perceptible delay. It's natural to assume that light simply is, that it appears instantly wherever it needs to be. In ancient times, most philosophers assumed exactly that. Aristotle, among others, believed light had no motion. It was simply a quality of the transparent medium between the eye and the object. Asking about the speed of light, in this view, was like asking about the speed of transparency, a category error, a question that didn't even make sense. But some thinkers weren't satisfied with this. In the 11th century, the Arab scientist Ibn al-Haytham, known in the West as Alhazen, argued that light must travel at a finite speed. He reasoned that, if it were instantaneous, there'd be no difference between seeing something immediately and seeing it after a delay. Yet, we clearly experience duration in visual perception, even if very brief. The first actual attempt to measure the speed of light came from Galileo in the early 1600s. His method was simple, if crude. He and an assistant stood on hilltops a mile apart at night, each with a shuttered lantern. Galileo would uncover his lantern, and when his assistant saw the light, he would uncover his own. Galileo would try to measure the time delay between uncovering his lantern and seeing his assistant's response. If light had a finite speed, there should be a measurable delay. There wasn't, or rather, the delay was far too short for human reaction time to measure. Galileo could only conclude that if light had a speed, it was very fast indeed. The breakthrough came in 1675 from an unlikely source: the moons of Jupiter. A Danish astronomer named Ole Romer was studying Io, one of Jupiter's large moons, which orbits the giant planet every 42.5 hours. Io regularly passes into Jupiter's shadow, disappearing from view in what's called an eclipse. These eclipses happen like clockwork, and they're easy to predict once you know Io's orbital period. But Romer noticed something odd. When Earth was moving toward Jupiter in its own orbit around the Sun, the eclipses happened slightly earlier than predicted. When Earth was moving away from Jupiter, they happened slightly later. The pattern was consistent and predictable. But why would the timing depend on Earth's position? Romer's explanation was elegant. Light takes time to travel across space. When Earth is closer to Jupiter, light from Io has less distance to cover, so the eclipse appears to happen earlier. When Earth is farther from Jupiter, light has more distance to cover, so the eclipse appears to happen later. The eclipses themselves were happening exactly on schedule. What was changing was how long it took the light from those eclipses to reach us. Romer calculated that light took about 22 minutes to cross the diameter of Earth's orbit. That's twice the Earth-Sun distance, since we're talking about Earth on opposite sides of its orbit. That wasn't quite right. The actual time is about 17 minutes. But he'd established something profound, something that would transform physics. Light has a speed. It's not infinite. It moves through space at a finite velocity, and that velocity can be measured. Over the following 2 centuries, scientists refined this measurement. In the 1700s, James Bradley used the phenomenon of stellar aberration, the apparent change in a star's position due to Earth's motion through space, to calculate light's speed. In the 1800s, Hippolyte Fizeau and Léon Foucault used rotating mirrors and toothed wheels to measure light speed in laboratories on Earth, avoiding the need for astronomical observations entirely. By the late 19th century, they knew the speed very precisely, about 300,000 kilometers per second. But knowing the speed and understanding what it meant were two different things. For most of the 19th century, physicists thought they understood light pretty well. Light, they believed, was a wave that much had been established by experiments showing interference and diffraction. And waves, as everyone knew, needed a medium to travel through. Sound waves travel through air. Water waves travel through water. Ocean waves travel through ocean. So light waves, clearly, must travel through some medium too. They called this medium the luminiferous ether. The ether was thought to fill all of space, a kind of transparent, massless substance that light waves rippled through. And just as you can measure your speed relative to the air through which sound travels, you should be able to measure your speed relative to the ether through which light travels. Earth is moving through space. It orbits the Sun at about 30 kilometers per second. And if Earth is moving through the ether, then light traveling in the direction of Earth's motion should move slightly faster, adding the ether wind to its speed, while light traveling perpendicular to Earth's motion should move at its normal speed. The difference would be small, but with careful measurements, it should be detectable. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect Earth's motion through this ether. They built an incredibly sensitive instrument called an interferometer, which split a beam of light and sent it along two perpendicular paths before recombining them. If light traveled at different speeds in different directions due to the ether wind, the two beams would arrive at slightly different times, creating an interference pattern that would shift detectably as the apparatus was rotated. They expected to see this shift. They designed their experiment specifically to detect it. They took meticulous measurements, and they found nothing. No shift, no difference. Light traveled at exactly the same speed regardless of which direction they measured or how the Earth was moving. They repeated the experiment at different times of year when Earth was moving in different directions through space. The results were always the same. The the speed of light was constant, independent of Earth's motion. This was baffling. It violated everything they thought they knew about how waves should behave. It was as if you were swimming in a river, and you found that swimming upstream took the same effort and speed as swimming downstream. Clearly impossible if there's a current. And yet, that's what the Michelson-Morley experiment showed for light. Some physicists tried to explain this away. Maybe the experimental apparatus physically contracted in the direction of motion through the ether, perfectly compensating for the time difference? That seemed awfully contrived. The results sat uncomfortably for nearly 2 decades, a puzzle that no one could quite solve. Enter Albert Einstein, a 26-year-old patent clerk working in Bern, Switzerland. In 1905, Einstein published a paper with an unassuming title, On the Electrodynamics of Moving Bodies. In it, he proposed something radical, something that would change physics forever. What if, Einstein asked, the speed of light is constant for all observers, regardless of how they're moving, not approximately constant, allowing for small variations, not constant within measurement error. Exactly, precisely, fundamentally constant. What if this isn't just a property of light, but a fundamental feature of space-time itself? What if the universe is built in such a way that the speed of light must be the same for everyone, always, no matter what? This seems impossible at first. It violates our everyday intuitions about how motion works. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour relative to the train. Someone standing on the platform watching the train pass would see the ball moving at 120 kilometers per hour. Your speed plus the ball's speed relative to you. This is common sense. This is how velocities add in everyday life. You learn this intuitively as a child, throwing things from moving swings or tossing a ball while running. But Einstein said, what if light doesn't work that way? Imagine instead that you're on a spaceship moving at 99% the speed of light. Let's call this 0, 99c, where c is the speed of light. You shine a flashlight forward. According to common sense, the light from your flashlight should be traveling at c plus 0, 99c, which would be 1, 99c, nearly twice the speed of light. But it doesn't. According to Einstein, and according to every experiment ever done, the light from your flashlight travels at exactly c, the normal speed of light. The person you're flying toward measures the speed of your flashlight's beam and gets c. You, inside the spaceship, measure the speed of your flashlight's beam and also get c, the same speed, always. How is this possible? How can the light not be going faster when you're already moving at 99% of light speed? Einstein's answer is as elegant as it is strange. Time and space must be flexible. They must adjust themselves to keep the speed of light constant. If you're moving relative to someone else, time must flow at different rates for you and them. Space must contract in the direction of motion. These aren't optical illusions or measurement errors. They're real, physical effects. Time genuinely, actually passes more slowly for moving objects. Distances genuinely, actually contract, and these effects become more dramatic as you approach the speed of light. This is the theory of special relativity, and it's been confirmed by countless experiments over the past century. Particles in accelerators moving at near light speed take longer to decay, exactly as the equations of relativity predict. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground by precisely the amount special relativity predicts. GPS satellites have to account for relativistic time dilation to maintain accurate positioning. Without corrections for relativity, GPS would accumulate errors of several kilometers per day. The implications are profound. Space and time, which we think of as separate things, are actually intimately connected, woven together into what Einstein called space-time. Motion through space affects motion through time. The faster you move through space, the slower you move through time, in such a way that the speed of light remains constant for everyone. And this leads to one of the most important conclusions in all of physics. Nothing with mass can travel at the speed of light. Here's why. As you accelerate an object, you're adding energy to it. Einstein showed that energy and mass are equivalent. That's what his famous equation E=mc² means. As something moves faster, it effectively gains mass. The faster you push it, the more massive it becomes from the perspective of anyone who's not moving along with it, and the harder it becomes to accelerate it further. As you approach the speed of light, the object's effective mass approaches infinity. It's impossible. It would require more than infinite energy, which isn't just difficult, it's meaningless. A logical contradiction. But light itself, photons, the particles of light, have no mass. Zero. Nothing. And because they have no mass, they don't need energy to maintain their speed. They're born, in a sense, traveling at light speed. And they never slow down, never speed up. They always move at c. That's just what they do. What they are, the only mode of existence photons know. Light speed isn't really about light at all, in a deeper sense. It's better thought of as the speed of causality, the maximum speed at which cause can lead to effect, at which information can propagate through space. It's the conversion factor between space and time in the equations of relativity. It's woven into the very fabric of space-time itself. And here's one more strange implication. If you could go faster than light, you could, in principle, travel into your own past. Effects could happen before their causes. The logical structure of cause and effect that we rely on, that underpins all of science, all of rationality, would break down. The universe, it seems, has set this speed limit not arbitrarily, but because it's necessary to maintain the coherence of physical law, the flow of time from past to future. Why does the universe have this particular speed limit? Why is c exactly 299,792,458 meters per second, and not some other value? It appears to be a fundamental constant of nature, built into the structure of reality itself at the deepest level we can access. We hope that someday, a deeper theory of physics, perhaps quantum gravity, perhaps something we haven't imagined yet, will explain why the speed of light has the value it does. But for now, we simply observe that this is how the universe works. The speed of light isn't just the speed at which light travels. It's the cosmic speed limit, the speed of causality, the thing that prevents effects from happening before their causes. It's the conversion factor between space and time. It's fundamental to the structure of space-time itself. And it's this speed, this unchanging, universal constant, that gives us our measuring stick for cosmic distances. Because if light always travels at the same speed, and we know that speed precisely, then we can convert time into distance. We can ask, how far does light travel in a second? In a day? In a year? In a million years? That question leads us directly to the concept of the light year itself, the natural unit for describing cosmic distances. The term light year trips people up sometimes. They hear year and think it must be a measure of time. It's no more a measure of time than meter is a measure of time, even though meters are defined by how far light travels in a specific fraction of a second. So let's do the mathematics. Light travels at 299,792 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. And the International Astronomical Union defines a light year using a Julian year, which is exactly 365 and 1/4 days. This keeps the definition clean and avoids the complications of leap years. Multiply it all out, and you get 9 trillion, 460 billion, 730 million, 472,580.8 kilometers. That's 1 light year, or in miles, about 5.88 trillion. These numbers are so large they almost lose meaning. 9.5 trillion kilometers. What does that even look like? How do you picture that? Let's try some comparisons. The distance from Earth to the Sun is about 150 million kilometers. Astronomers call this an astronomical unit, or AU, and it's a convenient measure for distances within our solar system. 1 light year equals about 63,241 astronomical units. Put another way, the distance light travels in 1 year is the same as going from Earth to the Sun more than 63,000 times. Here's another way to think about it. If you could travel at the speed of a commercial airplane, about 900 kilometers per hour, it would take you about 17 years to fly the distance from Earth to the Sunday. To cover 1 light year at that speed would take more than 1,000,000 years. 1,000,000 years of continuous flight, never stopping, never slowing down. The term light year itself has an interesting history. The first person to calculate the distance to a star other than the Sun was Friedrich Bessel, a German astronomer who, in 1838, measured the distance to a star called 61 Cygni. He used a technique called parallax, which we'll talk about more later, and he calculated that the star was about 660,000 astronomical units away. That's about 10.5 light years, though Bessel didn't use that term. He did note, almost poetically, that light takes about 10.3 years to traverse this distance. He knew his readers would find this easier to grasp than vast numbers of astronomical units, but Bessel hesitated to actually use light year as a formal unit. He was concerned that it might reduce the apparent precision of his measurements, since the speed of light wasn't known as accurately then as it is now. The term light year first appeared in print in 1851 in a German popular astronomy article by Otto Uhle. Uhle explained the oddness of a distance unit with year in its name by comparing it to a walking hour, a common German expression for the distance one could walk in an hour. Just as a walking hour describes distance in terms of travel time, so does a light year. For a while, professional astronomers resisted the term. Some called it inconvenient and irrelevant, preferring more technical units like the parsec, which is about 3.26 light years and is based on the geometry of stellar parallax measurements. But the light year caught on in popular usage because it's intuitive. Everyone can grasp the concept of how far something travels in a year, even if the actual distance defies imagination. Today, professional astronomers do tend to use parsecs for technical work, but light years remain the preferred unit for communicating with the public. There's something satisfying about the symmetry. A light year for distance, a year for time. It makes the connection between space and time feel more tangible. So let's get a sense of the scale we're dealing with. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. We live 8 light minutes from our star. If the Sun suddenly vanished, we wouldn't know for 8 minutes. We'd keep orbiting an empty point in space, basking in sunlight that was already on its way to us when the Sun disappeared, unaware that our star was gone. The nearest star to our Sun is Proxima Centauri, a small red dwarf that's part of the Alpha Centauri system. Proxima is 4.24 light years away. That means when you look at Proxima Centauri, you'd need a telescope. It's too faint to see with the naked eye. You're seeing it as it was 4 years and 3 months ago. If an alien civilization around Proxima Centauri pointed a telescope at Earth right now, they'd see Earth as it was in the year 2021. Any message we sent to them would take 4.24 years to arrive. Their reply would take another 4.24 years to get back. A conversation with our nearest stellar neighbors would require 8.5 years for each exchange. Our galaxy, the Milky Way, is a vast disk of stars, gas, and dust. The center of our galaxy, around which our solar system orbits, is about 26,000 light-years away. The light you see from the galactic center left when early humans were painting on cave walls, long before the invention of writing, agriculture, or civilization. The Andromeda Galaxy, that faint smudge you can see on a dark night, is 2.5 million light-years away. It's the most distant object visible to the naked eye. The light you see left Andromeda when our ancestors were just beginning to use stone tools. The intervening time saw the entire evolution of our species. And these are our neighbors. The observable universe extends billions of light-years in every direction. There are galaxies so distant that their light has been traveling toward us since shortly after the universe began, 13.8 billion years ago. The distances are so vast that kilometers and miles become absurd units to use. Even astronomical units, useful within our solar system, become unwieldy. The light year is the natural unit for cosmic distances because it respects the fundamental connection between space and time, between distance and the speed at which information travels. But understanding what a light year measures is one thing. Actually measuring these distances is quite another. We can't stretch a ruler across interstellar space. We can't time how long it takes a spacecraft to reach a distant star at our current speeds. It would take tens of thousands of years to reach even the nearest ones. So how do we know these distances? How did astronomers build their cosmic measuring stick? The answer is both ingenious and beautiful. Measuring distances in astronomy is fundamentally different from measuring distances on Earth. You can't send someone with a measuring tape to a star. You can't bounce a laser off a galaxy and time how long it takes to return. Instead, astronomers developed a series of methods, each one extending the reach of the previous one, each one calibrated using the method before it. This interconnected system is called the cosmic distance ladder. The beauty of the ladder is that each rung depends on the one below it, and together they allow us to measure distances across the entire observable universe. But like any ladder, if the bottom rungs are unstable, everything above becomes uncertain. So let's start at the bottom, with the most fundamental and reliable method, parallax. Hold your arm out in front of you and extend your thumb. Now close your left eye and look at your thumb with your right eye. Note where your thumb appears against the background. Now close your right eye and open your left. The closer the object, the bigger the parallax shift. Hold your thumb close to your face and repeat the experiment, and the shift is dramatic. Hold it at arm's length, and the shift is smaller. Astronomers use this same principle to measure distances to nearby stars, but instead of using two eyes a few centimeters apart, they use Earth's entire orbit as their baseline. They photograph a nearby star in January, when Earth is on one side of the sun, and again in July, when Earth is on the opposite side. The baseline is now 300 million kilometers, the diameter of Earth's orbit. Against the background of much more distant stars, the nearby star appears to shift position very slightly. The shift is tiny. Even for the nearest stars, it's less than 1 arcsecond, 1/3600th of a degree. Imagine looking at a coin from 2 kilometers away and trying to measure its width. That's the kind of precision we're talking about. But with modern instruments, we can do it. The first successful parallax measurement was made by Friedrich Bessel in 1838 for 61 Cygni. This was a monumental achievement. For the first time in history, we had a direct measurement of the distance to a star. It proved that stars were indeed at vast distances, far beyond anything that could be measured in astronomical units alone. For most of the 20th century, parallax measurements were limited by the blurring effects of Earth's atmosphere. Ground-based telescopes could measure parallax reliably only for stars within a few hundred light-years. But in 1989, the European Space Agency launched a satellite called Hipparcos, designed specifically to measure stellar parallax from above the atmosphere. Hipparchus measured the positions and parallaxes of more than 100,000 stars with unprecedented precision, extending reliable parallax measurements to about 1,600 light-years. Then came Gaia, Hipparchus's successor. Launched in 2013, Gaia is revolutionizing our understanding of the Milky Way. It's measuring the positions, distances, and motions of more than 1 billion stars, about 1% of all the stars in our galaxy. Its precision is extraordinary. It can measure angles to within micro-arc seconds. To give you a sense of that precision, if you placed Gaia on top of Buckingham Palace, it could measure the width of a human hair on top of the Empire State Building, more than 5,500 kilometers away. Gaia's parallax measurements extend to stars several thousand light-years away, giving us a detailed three-dimensional map of our stellar neighborhood. But even Gaia has limits. Beyond a few thousand light-years, parallax angles become too small to measure reliably. The angles are there, but they're buried in the noise of measurement uncertainty. So we need another method, one that can reach farther. This is where the concept of standard candles comes in. Imagine you're standing in a field at night and you see two distant streetlights. One appears brighter than the other. Why? It could be that one light is genuinely brighter, a more powerful bulb, or it could be that both lights are identical, but one is closer to you. The fainter one must be farther away. And if you knew the exact brightness of the bulbs, their intrinsic luminosity, you could calculate their actual distances. This is the principle behind standard candles. A standard candle is any astronomical object whose intrinsic brightness is known. By comparing this known brightness with how bright the object appears from Earth, we can calculate its distance using the inverse square law. Brightness falls off with the square of the distance. Double the distance and the brightness drops to 1/4. Triple the distance and it drops to 1/9. But here's the catch. How do we know the intrinsic brightness of a distant star? We need examples close enough that we can measure their distances using parallax, determine their true brightness, and then recognize similar objects at greater distances. This is exactly what Henrietta Swan Leavitt did in 1908, working at the Harvard College Observatory. Leavitt was studying variable stars, stars whose brightness changes periodically. Specifically, she was looking at Cepheid variables in the Magellanic Clouds, two small satellite galaxies orbiting the Milky Way. These clouds are far enough away that all the stars in them are effectively at the same distance from us. That meant Leavitt could compare the apparent brightness of different Cepheids without worrying about distance differences. She noticed something remarkable. There was a clear relationship between how long a Cepheid took to pulsate and how bright it was at maximum brightness. Cepheids with longer periods were intrinsically more luminous. This period luminosity relation was a game changer. If you could measure a Cepheid's pulsation period, which is easy to do, you just watch it over several days or weeks, you could determine its true luminosity. And once you knew its true luminosity, you could calculate its distance from how bright it appeared. The first step was calibrating the relationship using Cepheids in the Milky Way, whose distances could be measured by parallax. Once calibrated, Cepheid variables became cosmic lighthouses. They're bright enough to be seen in nearby galaxies, and their periods tell us their true brightness with good precision. Astronomers can identify Cepheids in galaxies millions of light-years away, measure their periods, calculate their luminosities, and determine the distances to their host galaxies. This technique was crucial in one of the great debates of early 20th century astronomy. Were the spiral nebulae distant galaxies like our own, or were they merely gas clouds within the Milky Way? In 1923, Edwin Hubble used Cepheid variables in the Andromeda Nebula to measure its distance. It was nearly 900,000 light-years away, far beyond the bounds of the Milky Way. Andromeda was indeed a separate galaxy. The universe was suddenly much larger than anyone had imagined. Cepheid variables can be seen and measured out to about 100 million light-years with large telescopes like the Hubble Space Telescope. But beyond that, even these luminous stars become too faint to detect reliably. We need something brighter. We need supernovae. Type Ia supernovae are among the most violent events in the universe. They occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the mass of the Sunday. At that point, the white dwarf collapses and then explodes, releasing energy equivalent to an entire galaxy for a few weeks. These explosions are so bright, they can be seen across billions of light years. What makes Type Ia supernovae excellent standard candles is that they all reach roughly the same peak brightness. This happens because they all involve white dwarfs exploding at the same critical mass. There's some variation, but astronomers have learned to correct for it by studying the light curves, how the brightness changes over time. With these corrections, Type Ia supernovae become remarkably consistent standard candles. Because they're so bright, Type Ia supernovae can be seen at enormous distances. They've been detected in galaxies billions of light years away. In the 1990s, two independent teams used Type Ia supernovae to measure distances to far-flung galaxies, and they discovered something astonishing. The universe's expansion is accelerating. Distant supernovae were fainter than expected, meaning their galaxies were farther away than they should have been if the universe were expanding at a constant rate. This discovery led to the concept of dark energy and earned the team leaders the Nobel Prize in Physics in 2011. The cosmic distance ladder has more rungs than just these. There are techniques like the Tully-Fisher relation, which connects a galaxy's rotation speed to its luminosity, allowing distance measurements from Doppler shift observations. There are planetary nebula luminosity functions, surface brightness fluctuations, and gravitational lensing time delays. Each method has its strengths and limitations, its range of applicability, but there's one more technique we need to discuss, one that extends to the edge of the observable universe: redshift. When a light source moves away from you, its wavelengths are stretched, shifted toward the red end of the spectrum. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound lower pitched as it drives away. In astronomy, redshift is how we measure the velocities of distant objects. In 1929, Edwin Hubble made another groundbreaking discovery. He observed that nearly all galaxies showed redshifts, meaning they were all moving away from us. More remarkably, the farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, revealed that the universe itself is expanding. Space is stretching, carrying galaxies apart like raisins in a rising loaf of bread. For very distant galaxies, this cosmological redshift becomes the primary way we describe distance. We can't always use standard candles at such extreme distances. Even supernovae become difficult to detect. But we can measure redshift from the spectrum of light a galaxy emits. Combined with our understanding of cosmic expansion, redshift tells us how far away these galaxies are. The highest confirmed redshifts are now greater than 10, corresponding to galaxies we're seeing as they were less than 500 million years after the Big Bang. These are the most distant objects we've ever observed, their light having traveled more than 13 billion light years to reach us. The cosmic distance ladder, from parallax to cepheids to supernovae to redshift, allows us to measure distances across the entire observable universe. Each method extends our reach, while remaining anchored to the geometric certainty of parallax measurements to nearby stars. It's an elegant system, refined over more than a century of painstaking observations. But here's where things get truly mind-bending. These distances measured in light years tell us more than just where things are. They tell us when those things are. Every measurement of cosmic distance is simultaneously a measurement of cosmic history. Let's explore what that means. Light takes time to travel. This is such a simple statement, but its implications are profound. When you look at anything, you're not seeing it as it is now. You're seeing it as it was when the light left it. For objects nearby, this distinction is trivial. The light from a tree 10 meters away left that tree 33 nanoseconds ago. You're seeing the tree as it was 33 billionths of a second in the past. That's a delay so brief it's meaningless. But as distances grow, the delay becomes significant. And in astronomy, the delays become enormous. The sun is 8 light minutes away. When you watch the sunset, please don't look directly at it. You're watching the sun as it was 8 minutes ago. If something dramatic happened on the sun right now, if it suddenly dimmed or brightened, you wouldn't know for 8 minutes. The light you're currently seeing left the sun's surface before you started reading this sentence, traveled 93 million miles through the vacuum of space, and is just now entering your eyes. Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years away. The light you see from Proxima left that star in late 2021. If Proxima Centauri exploded today, we wouldn't see the explosion until 2030. For those 4 years, we'd continue seeing the star as it was, completely unaware that it no longer existed. This time delay, the difference between when light was emitted and when we observe it, is called lookback time. And as distances increase, lookback time stretches into the deep past. Consider the galaxy M87, home to the supermassive black hole whose shadow was famously photographed by the Event Horizon Telescope in 2019. M87 is about 55 million light-years away. When you look at images of M87, you're looking back 55 million years. The light left that galaxy during the Paleocene epoch on Earth, shortly after the extinction event that killed the dinosaurs. Early mammals were just beginning to diversify. The continents were still shifting into their current positions. And in M87, something happened. Perhaps the black hole consumed a particularly large meal. Perhaps stars formed in a burst of activity and photons were emitted that would eventually cross the universe to reach Earth. Those photons traveled through expanding space for 55 million years. They passed by galaxies, crossed vast voids, journeyed through regions where dark matter's gravity gently bent their paths. And finally, in April 2019, some of those photons entered the radio dishes of the Event Horizon Telescope and became part of human knowledge. But here's the crucial point. Whatever we're seeing in M87 happened 55 million years ago. The black hole we imaged might have consumed more matter since then. Stars that appear to be shining might have exploded. New stars might have formed. We have no way of knowing. We're observing the past, and we're forever out of date. This gets more dramatic the farther we look. The Hubble Space Telescope has photographed the Hubble Deep Field and its successors' tiny patches of sky, each one smaller than a grain of sand held at arm's length, yet filled with thousands of galaxies. Many of these galaxies are billions of light-years away. We're seeing them as they were billions of years ago, when the universe was younger, when galaxies were still forming and merging, when the first generation of stars was forging the first heavy elements. One galaxy, photographed in the Hubble Ultra Deep Field and later studied in detail, is called UD-Phi 3813559. It has a redshift of 8.6, corresponding to a lookback time of about 13.1 billion years. The light we detected from this galaxy left when the universe was only about 600 million years old, less than 5% of its current age. We're seeing this galaxy as it was in the cosmic dawn, when the first galaxies were just coalescing from the primordial gas that filled the early universe. But wait, if the light from UD-Phi 3813559 has been traveling for 13.1 billion years, does that mean the galaxy is 13.1 billion light-years away? Not quite. This is where things get truly strange, because the universe has been expanding while that light was traveling. When the light left the galaxy, it was much closer to us, or rather, to the region of space that would eventually become the Milky Way. But space itself was expanding, and that expansion carried the galaxy farther away even as its light was crossing the intervening distance toward us. Today, if we could somehow see UDF 381-355-39 as it currently exists, which we can't because we can only see its ancient light, it would be about 30 billion light-years away. The light travel distance is 13.1 billion light-years. The actual distance now, the co-moving distance accounting for cosmic expansion, is more than twice that. This distinction between light travel time and actual distance becomes crucial at cosmic scales. But the concept of lookback time isn't just a curiosity. It's a scientific tool of immense power. It allows us to study the history of the universe by observing objects at different distances. Want to know what galaxies looked like a billion years ago? Look at galaxies a billion light-years away. Want to see the universe as it was 10 billion years ago? Find galaxies 10 billion light-years distant. We can't travel back in time, but we can observe the past by looking out into space. This is how astronomers study galaxy evolution. They observe nearby galaxies to see what mature galaxies look like today. They observe galaxies at intermediate distances, say 5 billion light-years, to see what galaxies look like in the universe's middle age. And they observe the most distant galaxies to see what the first galaxies looked like shortly after the Big Bang. By combining observations across this range of distances, across this sweep of look-back times, they can piece together the story of how galaxies form, grow, merge, and evolve over cosmic history. The James Webb Space Telescope, launched in late 2021, was designed specifically to study these distant, early galaxies. With its large mirror and infrared sensitivity, JWST can detect galaxies with redshifts greater than 10. Galaxies whose light has been traveling for more than 13 billion years. It's a time machine, not in the science fiction sense, but in the sense that it allows us to observe the deep past directly. There's something profound in this. Every telescope is a time machine. Every observation is an observation of the past. When you watch the moon, you see it as it was about 1.3 seconds ago, the light travel time from the moon to Earth. When you see Jupiter, you're looking back 35 to 52 minutes, depending on where Earth and Jupiter are in their orbits. When you observe the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. And the most distant light we can detect? That comes from the cosmic microwave background, the faint glow of radiation left over from when the universe was only 380,000 years old. This light has been traveling for more than 13 billion years. It's the oldest light in the universe, a baby picture of the cosmos taken when it was less than 1/30,000th of its current age. Every distance is a timestamp. Every light year is also a year back in time. Space and time are inseparably linked, not just in Einstein's equations, but in our observational experience of the universe. We cannot see distant space without seeing ancient time. We cannot observe out there without observing back then. This leads to a peculiar and humbling realization. There is no now that spans the universe. When you think about what's happening right now in the Andromeda Galaxy, you're asking a question that has no absolute answer. From our perspective, now in Andromeda is what we're currently observing, the light that's arriving at this moment, showing us Andromeda as it was 2.5 million years ago. But from the perspective of someone in Andromeda, now on Earth would be what they're observing of us, which is Earth as it was 2.5 million years ago. There's no universal present moment, no cosmic clock that synchronizes everything. The universe is not just vast in space, it's deep in time. And we, observing it, are always looking into history. The light year measures not just distance, but temporal separation. It quantifies how far back we're looking when we observe something far away. This is one of the most beautiful and strange aspects of astronomy. We study the past not by digging through ancient rocks or reading old documents, but by simply looking up. The farther we look, the further back we see. The universe has kept a record of its history written in light, and that light is still traveling toward us, carrying information about long ago events in distant places. But here's the final twist. Understanding these distances intellectually is one thing. Truly grasping them, feeling them in your bones, picturing them in your mind, that's something our brains simply cannot do. And there's a reason for that. Our brains are products of evolution, shaped over millions of years by the demands of survival in a specific environment. Our ancestors needed to judge the distance to a predator, estimate how far away water or food was, navigate through forests and across plains. They needed to understand space at the scale of meters to kilometers, distances they could walk in minutes to days. That's the spatial reality our cognitive systems evolved to handle. We're exquisitely good at it. Within that range, you can glance at a cup on a table and reach out to grab it with remarkable precision. You can estimate whether you can jump across a stream or whether you need to find another crossing. You can remember the layout of your home and navigate it in the dark. These abilities required sophisticated neural machinery, involving multiple brain regions working in concert to build and maintain our mental model of the space around us. But evolution had no reason to equip us with intuitions about light years. Our ancestors never needed to conceptualize distances of trillions of kilometers. Such distances had no bearing on survival or reproduction. And so our brains, for all their sophistication, simply aren't built to genuinely grasp cosmic scales. There's an interesting bit of research that illustrates this. Scientists have mapped the range of space and time that humans can directly perceive. They've plotted it on a logarithmic scale, where each step represents a tenfold change in size or duration. On this scale, the universe spans from subatomic particles at about 10 to the minus 15 meters to the observable universe at about 10 to the 26 meters. That's 41 orders of magnitude. Time spans from quantum events at about 10 to the minus 23 seconds to the age of the universe at about 10 to the 17 seconds. 40 orders of magnitude. Human perception fits into a tiny box in the middle of this graph. We can directly perceive objects from about 1/10 of a millimeter, roughly the width of a human hair, to perhaps 10 kilometers on a clear day, when we can see distant mountains. That's about 8 orders of magnitude out of the 41 that exist. We're perceiving less than 20% of the range of scales that matter in our universe. Time is similar. We can perceive events as brief as about 50 milliseconds, much shorter, and things blur together up to perhaps a human lifetime. Beyond that, we need records and history to comprehend longer timescales. This means that most of reality, most of the universe's range of scales, lies beyond our direct perception. We can measure it with instruments, we can calculate it with mathematics, we can understand it intellectually, but we can't feel it. We can't picture it. Not really. Try this thought experiment. Imagine a trillion of something. 1 trillion. Start counting. 1, 2, 3, 4. Count one number per second, never stopping. How long would it take you to reach a trillion? About 31,700 years. That's longer than recorded human history. If you'd started counting when the first cities were being built in Mesopotamia, you'd still be counting today, and you wouldn't be close to finished. And a trillion is just the number of kilometers in a single light year, well, about 1/10 of a light year. The actual number of kilometers in a light year is closer to 10 trillion. When numbers get this large, they cease to have intuitive meaning. The difference between a million, a billion, and a trillion gets compressed into really big without real differentiation. The distance to Andromeda is about 24 quintillion kilometers. Do you feel any difference between quintillion and trillion? Can you picture one being a million times larger than the other? We resort to analogies to try to build understanding. If the sun were the size of a grapefruit, Earth would be a grain of sand about 15 meters away. At that scale, Proxima Centauri would be another grapefruit about 4,000 kilometers away. That helps, maybe, to understand the relative scales within our solar system and to the nearest star, but push the analogy further, try to scale the entire galaxy or the distance to Andromeda, and the numbers become absurd again. The model no longer helps. Part of the problem is that our mental representation of distance is not linear. Research on cognitive distance perception shows that humans systematically distort distances beyond familiar scales. We perceive space logarithmically, not linearly. The difference between 10 and 100 feels about the same as the difference between 100 and 1000. Each tenfold increase feels like one step, not 10 times larger. This is actually a sensible way to handle a wide range of scales, but it means we can't truly feel the difference between a million and a billion. Both are compressed into very large in our intuitive understanding. And this compression becomes even more dramatic with astronomical distances. Neuroscience has revealed that different brain regions handle spatial cognition at different scales. Studies using functional MRI have shown that when people think about distances at room scale, certain regions of the brain are active. When they think about city scale or country scale, different regions become involved. There's a gradient of activation from posterior to anterior regions as the spatial scale increases, suggesting that our brains represent small-scale and large-scale space quite differently. What's more, the neural systems that handle familiar, navigable space, the kind of space you can walk through, are different from those that handle very large spaces you can only conceptualize abstractly. The hippocampus and surrounding regions, which are critical for navigation and spatial memory, show different patterns of activity for different spatial scales. We don't simply scale up our intuitions from room size to cosmic size. And beyond a certain scale, those processes stop being about intuition at all. They become purely abstract, symbolic, mathematical. You can know that the Andromeda galaxy is 2.5 million light-years away. You can understand what that means in terms of light travel time. You can work with the number in calculations, but you cannot picture it. You cannot feel it. Your brain has no framework for genuine comprehension at that scale. This isn't a failure of intelligence or education. It's a limitation built into our cognitive architecture. We are small beings trying to comprehend an incomprehensibly large universe. Our minds, shaped by evolution for an entirely different purpose, are doing their best with tools that were never meant for this task. There's a kind of intellectual vertigo that comes from really thinking about this. The distances we're discussing are not just big. They're not just bigger than anything in human experience. They're bigger than anything we can hold in our minds. We can describe them, measure them, compare them, but we cannot truly imagine them. The universe's scale transcends our capacity for intuitive understanding. And perhaps, in a way, that's appropriate. Why should the universe conform to human intuition? We're not the measure of all things. The cosmos doesn't care about the scale at which our brains happen to work. It operates at its own scales, from the quantum to the cosmic, and we're just one tiny part of it, trying to make sense of the whole. Some philosophers and scientists have suggested that this inability to grasp cosmic distances is a form of cognitive humility. It reminds us that there are aspects of reality that exist beyond our intuitive reach. We can know them, but we cannot feel them. We can measure them, but we cannot picture them. There is always something beyond our comprehension. Not because we're not smart enough, but because the universe is vaster than the mental models we're capable of constructing. But here's the beautiful part. We don't need intuition to understand. Mathematics extends where intuition fails. Instruments extend where perception fails. We can measure things we cannot see, calculate things we cannot imagine, and know things we cannot picture. The light year is one of those tools, a unit that connects the knowable to the incomprehensible, that allows us to describe with precision what we cannot truly grasp with our minds. And maybe that's enough. Maybe it's not a limitation, but an invitation. An invitation to accept that we're small, that the universe is vast, that some things will always be beyond our intuitive grasp. And that's okay. It doesn't diminish us. If anything, it elevates us. We're the species that can measure what it cannot imagine, that can know what it cannot feel, that can reach with mathematics and observation far beyond the boundaries of human scale experience. There's a peace in accepting this, in letting go of the need to picture everything, to hold it all in your mind. The universe is larger than your mind can accommodate, and that's not a problem. It's just how things are. We've journeyed far tonight, from the speed of light to the farthest reaches of the observable universe, from the careful measurements of parallax to the profound strangeness of lookback time. We've confronted the limits of human intuition and found both humility and wonder in those limits. So what does it all mean? What do these vast distances, these incomprehensible scales tell us? First, they tell us something about our place. The universe is not built at human scale. It never was. For most of human history, we imagined ourselves at the center of creation, with everything revolving around us. The sun, the moon, the stars, all were thought to exist for our benefit. We're not special in location or in scale. We're inhabitants of an ordinary planet, orbiting an ordinary star, in an ordinary galaxy, in a universe so vast that our entire galaxy is just one of hundreds of billions. The distance to Andromeda alone, 2.5 million light-years, is greater than all of recorded human history by a factor of thousands. The observable universe extends billions of light-years in every direction, a sphere so large that light from its edges has been traveling since shortly after the beginning of time itself. We are, in cosmic terms, vanishingly small. A human being compared to Earth is as Earth compared to the Sun, as the Sun compared to a light year, as a light year compared to the observable universe. We're nested within scales of largeness that dwarf us again and again. But there's another side to this. Yes, we're small, but we're also the beings who measured it. We're the creatures who looked up at the night sky and wondered, who built telescopes and satellites, who developed mathematics and physics, who conceived of parallax and standard candles and cosmic expansion. We're the species that can look at a faint smudge of light and deduce that it's a galaxy of hundreds of billions of stars, 2.5 million light-years away. We're the beings who can detect light that's been traveling for 13 billion years and extract from it information about the early universe. We're small, yes, but we're also magnificent in our curiosity, our ingenuity, our refusal to accept ignorance. Light connects us to this vastness. Every photon that enters your eye is a messenger. The light from the stars has crossed impossible distances to reach you. That light has traveled through the near-perfect vacuum of space, perhaps for thousands or millions of years, largely undisturbed. And at the end of its journey, it arrives at your eye and triggers a cascade of neural signals that let you see. You are touching, in a very real sense, the distant universe. The photons bringing you information about a star 1,000 light-years away left that star 1,000 years ago, traveled across the galaxy, and ended their journey by interacting with molecules in your retina. You're connected to that ancient starlight by the most intimate of contacts, It literally becomes part of your experience. This is true for every star you see. Every point of light in the night sky is sending you a message from the past, carried by photons across the light years. When you look up, you're not just seeing the universe as it is, you're seeing it as it was, across a range of lookbacks, times from minutes to millennia, all simultaneously. The light from the sun is 8 minutes old. The light from Sirius is 8.5 years old. The light from the center of the Milky Way is 26,000 years old. The light from Andromeda is 2.5 million years old. All of this ancient light, all these photons from different eras, arrive at your eyes in the same moment, creating a view of the cosmos that spans time as well as space. There's something profoundly beautiful about this. Light is the thread that stitches the universe together. It's the carrier of information, the messenger that brings us knowledge of distant places and times. Without light, we'd know almost nothing about the cosmos beyond our immediate vicinity. But with light, and with our understanding of how it travels, we can reach across the universe. We can see the births of stars, the deaths of galaxies, the echoes of the Big Bang itself. And these observations aren't just aesthetic or philosophical. They're practical, scientific, crucial to our understanding of reality. The distances we've measured using light years have revealed the structure of the universe, the rate of its expansion, the distribution of matter, the existence of dark matter and dark energy. When astronomers measured distances to Type Ia supernovae and found them farther away than expected, they discovered that the universe's expansion is accelerating, a discovery that revolutionized cosmology and raised profound questions about the nature of reality that we're still grappling with today. The Hubble constant, the rate at which the universe expands, is measured in kilometers per second per megaparsec, a unit that explicitly connects velocity to distance. Get the distances wrong, and you get the expansion rate wrong. Get the expansion rate wrong, and you misunderstand the age of the universe, its ultimate fate, the nature of dark energy. Cosmic distance measurements aren't just interesting trivia. They're foundational to our entire cosmological worldview. And yet, for all this scientific importance, there's still poetry in it. There's still wonder. The fact that we can measure these distances doesn't make them less awesome. If anything, it makes them more so. We know now, with precision, how far away things are, and that knowledge reveals the true scale of the universe in a way that vague guesses never could. The universe is not just very big. It's specifically, measurably big. It's 9.46 trillion kilometers per light year, times billions of light years in every direction. That specific bigness is more humbling than vague enormity ever could be. And the distances keep growing. With every new generation of telescopes, we see farther, earlier, deeper into space and time. The James Webb Space Telescope is already detecting galaxies farther away than anything we've seen before. Future telescopes will push even farther, perhaps even detecting the first stars that formed in the universe, ending the cosmic dark ages. We'll measure distances that correspond to look-back times of 13.6 billion years, seeing the universe as it was less than 200 million years after the Big Bang. Each new measurement is a triumph of human curiosity and capability. Each one pushes the boundary of our knowledge a little farther out, and each one reminds us, again and again, of the sheer scale of the cosmos we inhabit. But perhaps most importantly, understanding cosmic distances gives us perspective. When you grasp or try to grasp that the observable universe is 93 billion light years across, that light from the farthest objects has been traveling longer than Earth has existed, that the Milky Way is just one of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which likely have planets. When you sit with that knowledge, really sit with it, it changes something. It makes your worries seem smaller. not unimportant, not trivial, but smaller. Placed in cosmic context, the things that loom large in your daily life, the deadlines, the conflicts, the anxieties shrink to their proper size. You're a temporary being on a small planet, experiencing a brief flicker of consciousness in a cosmos that will continue for trillions of years after you're gone. That could be terrifying, or it could be liberating. The philosopher Carl Sagan called this the pale blue dot perspective, named for the photograph of Earth taken by Voyager 1 from the edge of the solar system. In that photo, Earth is less than a pixel, a pale blue dot against the black of space. Sagan wrote, "On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam." That's the cosmic perspective. That's what understanding distance gives us. And yet, paradoxically, we're the local phenomena that can comprehend the global, the temporary beings that can think about eternity. Consciousness is rare, as far as we know. Intelligence is precious. The fact that we exist at all, that the universe has organized itself in such a way that parts of it can think about the whole, that's extraordinary. So when you look up at the stars tonight, remember, you're seeing light that has crossed light years to reach you. You're connected, by photons and by understanding, to a cosmos vastly larger than yourself. And you're the being capable of knowing this, of measuring it, of finding meaning in it. The light year is more than a unit of distance. It's a reminder of how far we've come, both literally and metaphorically, in our understanding of the universe. It's a tool that allows us to describe the indescribable, to quantify the unimaginable. And it's an invitation to humility, to wonder, to curiosity, to the recognition that we're part of something magnificent, something far larger than ourselves, something worth contemplating as we drift off to sleep beneath an ancient, patient sky. As we come to the end of this journey, let's take a moment to reflect on where we've been. We started with a simple question: what is a light year? And in answering it, we've traversed the cosmos, from the fundamental nature of light itself to the farthest reaches of the observable universe. We've seen that light travels at a specific, unchanging speed, and that this speed is more than just a physical property. It's the cosmic speed limit, the conversion factor between space and time, the foundation of relativity itself. We've learned that a light year, despite its name, is a distance. The distance light travels in 1 year, 9.46 trillion kilometers, a number so large it defies intuition. We've discovered how astronomers measure these vast distances, building a cosmic distance ladder from parallax to standard candles to redshift, each rung extending our reach farther into space. We've seen how parallax uses geometry to measure nearby stars, how Cepheid variables and supernovae serve as cosmic lighthouses visible across millions and billions of light years, and how the expansion of the universe itself becomes a measuring tool at the grandest scales. We've confronted the strange truth that every measurement of distance is also a measurement of time, that looking out into space is looking back into history. We've understood that the light entering our eyes is ancient, that we're seeing the sun as it was 8 minutes ago, Andromeda as it was 2.5 million years ago. We've realized that astronomy is a form of time travel, not into the future, but into the past, and that every telescope is a time machine. And we've faced the humbling recognition that our brains, shaped by evolution for entirely different purposes, cannot truly grasp these scales. We can know them, measure them, describe them, but we cannot picture them, cannot feel them intuitively. The universe is larger than our minds can hold, and that's okay. It's an invitation to humility, to the recognition that some things transcend intuition, that mathematics and observation extend where perception fails. But the story doesn't end here. Even as I speak, even as you listen, the cosmos continues its work. Galaxies are forming, stars are being born and dying, light is traveling across the incomprehensible distances between them. The Gaia satellite is still measuring stellar parallaxes, refining our map of the Milky Way, pushing the reach of geometric distance measurements a little bit farther. The James Webb Space Telescope is detecting the faint light of galaxies formed in the first few 100 million years after the Big Bang, pushing the boundaries of look-back time. There are still mysteries. We don't fully understand dark energy, the force that's accelerating the universe's expansion. We're still refining our measurements of the Hubble constant. We're still discovering new ways to measure cosmic distances, new standard candles, new techniques that might extend our reach even farther. Every generation of astronomers climbs a little higher on the cosmic distance ladder. Every new instrument extends our vision a little deeper into space and time, and each step reveals new wonders, new questions, new aspects of the universe we hadn't known to ask about. But you don't need a telescope to participate in this. You don't need to be an astronomer to experience the wonder of cosmic distance. The next time you're under a clear night sky, take a moment to really look. Pick a bright star, maybe Sirius, the brightest star in the night sky, 8.5 light years away. The photons entering your eye left that star 8.5 years ago. They've been traveling through space all that time, crossing the light years, and they've just now reached you. You're seeing a message from the past, delivered by light. Or look for Andromeda, that faint smudge visible on dark autumn nights in the northern hemisphere. Remember, you're seeing that galaxy as it was 2.5 million years ago. When that light left Andromeda, your ancestors were just learning to make the first crude tools. The entire span of human civilization, everything we've built and written and discovered, has occurred in the time it took that light to cross the space between galaxies and reach your eyes. There's a comfort in this perspective. Your worries, your struggles, your daily concerns, they're real, they matter to you, but placed against the backdrop of cosmic distance and time, they're also small, temporary, part of the brief, flickering moment that is your conscious experience in a universe that existed for billions of years before you and will continue for billions more after you're gone. This isn't meant to diminish your experience. It's meant to contextualize it. You're a small part of something vast and ancient and magnificent. You're made of atoms forged in stars that exploded billions of years ago. Atoms that somehow organized themselves into a form capable of looking back at those stars and understanding them. You're the universe experiencing itself, becoming aware of itself, measuring itself, and in that awareness, in that capacity for understanding, there's meaning. It doesn't matter that you can't intuitively grasp a light year. It matters that you can know what it means, that you can think about it, that you can place yourself in context. That ability, that consciousness, is precious and rare as far as we know. You're one of the lucky ones, aware and curious and capable of wonder. So as you drift toward sleep tonight, beneath a sky full of ancient light, remember, those photons have traveled vast distances to reach you. The universe is larger than you can imagine, older than you can picture, more complex than you can comprehend. And yet, here you are, a small being on a small planet, trying to understand it all. And succeeding, at least in part. Rest well, knowing that the cosmos continues its patient work. Stars are still shining, light is still traveling, the cosmic distance ladder is still extending our reach. And tomorrow, or next week, or next year, we'll learn something new, see something farther, understand something deeper. The journey continues. The light travels on, and you've been part of it. If this exploration of cosmic distances resonated with you, If it brought you a moment of wonder or peace, I'd be deeply grateful if you'd consider leaving a like on this video. It helps others find these explorations of the cosmos, these late-night journeys through space and time and understanding. And if you'd like more content like this, more long-form explorations of the universe designed to educate and soothe, to inform and inspire, consider subscribing. Your support means the world to me and allows me to continue creating these deep dives into the cosmos. But whether you subscribe or not, whether you like this video or not, thank you for spending this time with me. Thank you for your curiosity, your attention, your willingness to think about light years and cosmic distances, and the strange, wonderful fact that we can measure what we cannot imagine. Sleep well, dream of starlight, and remember, the universe is vast, but you're part of it, and that's something worth marveling at. Good night.